Imagine holding a simple teaspoon in your hand. Now imagine scooping up a tiny bit of material from a distant, glittering object in the cosmos. If that object were a neutron star, the substance in your spoon would weigh billions of tons. That's right, a single teaspoonful of a neutron star would have the same mass as all of humanity combined. A single teaspoonful would equal a mountain like Mount Everest, all of that crushed down into a volume no bigger than a sugar cube. This isn't science fiction. This is one of the most extreme and fascinating realities our universe has to offer. It's a place where the familiar rules of matter are broken and reformed into something almost beyond our imagination. What kind of object could possibly be so dense? It's not a planet. It's not a star like our sun. It's the ghost of a star. A neutron star is what's left behind after a massive star, one much larger than our own, lives its life and dies in a spectacular explosion. This stellar remnant is one of the smallest, densest objects known to exist in the cosmos. It's a city-sized sphere packed with more mass than our entire sun. To truly grasp this, think about taking our sun, which is over 1,000,000 times the volume of Earth, and squeezing it down until it fits into an area smaller than Manhattan Island. How does such a bizarre object come into being? Its story begins with a star, but not just any star. It must be a massive one, at least 8 times more massive than our sun. For millions of years, this stellar giant burns brightly in the cosmic dark, fusing lighter elements into heavier ones. It's a cosmic forge, creating elements like carbon-oxygen iron. Nuclear fusion generates a tremendous outward pressure. That pressure holds the star up, fighting the inward pull of its own gravity. A delicate balance that defines the star's life. But the balancing act cannot last forever. The core builds up iron. Fusing iron doesn't release energy. It consumes it. The furnace at the heart of the star suddenly shuts down. With fusion gone, gravity wins in an instant. The core collapses catastrophically under its own weight. In less than a second, a region the size of Earth is crushed to a ball just a few miles across. The collapse rebounds, a shock wave blasts the outer layers into space. This spectacular explosion is called a supernova. For a brief time, the dying star can outshine its entire galaxy, a brilliant beacon across millions of light years. One of the most energetic events in the universe. A neutron star is not just dense, it is a realm where the fundamental forces of nature are amplified to an almost unbelievable degree. Let's start with its gravity. Because it packs so much mass into such a tiny space, the gravitational pull on the surface of a neutron star is staggering. It is about 200 billion times stronger than the gravity you feel on Earth. If you could somehow stand on its surface, you would be instantly flattened into a microscopic film of atoms. Even light itself struggles to escape its grasp, its path visibly bent by the star's gravitational field. This extreme gravity also has a profound effect on the neutron star's landscape. The surface of a neutron star is the smoothest place in the universe. The intense gravitational pull crushes any mountains or surface features down to mere fractions of an inch. If you were to scale up a neutron star to the size of our planet, the tallest mountain on its surface would be less than a centimeter high. The star is an almost perfect sphere, a polished remnant of cosmic collapse where the force of gravity reigns supreme and tolerates no imperfections on its super-smooth solid crust. But gravity isn't the only force that gets dialed up to 11. Neutron stars also possess some of the most powerful magnetic fields in the cosmos. As the original star's core collapsed, its magnetic field was compressed and intensified to an incredible degree. A typical neutron star's magnetic field is 1 trillion times stronger than Earth's. A special type, known as a magnetar, can have a magnetic field 1,000 times stronger still. This field is so powerful that it could wipe the data from every credit card on Earth from halfway to the moon. It's a force so intense, it can distort the shapes of atoms themselves. These extreme properties make neutron stars fundamentally different from anything else we know. In 1967, a young astronomer named Jocelyn Bell Burnell was scanning the skies with a new radio telescope. She detected a strange signal, a pulse that repeated with astonishing regularity once every 133 seconds. At first, the team joked they might have found aliens, labeling it LGM-1 for Little Green Men. they soon found other, similar signals from different parts of the sky. They had not found aliens, they had discovered a new type of celestial object. The source of these cosmic beats was a spinning neutron star, a pulsar. So why do they pulse? A neutron star forms from the collapse of a spinning star conserving angular momentum, much like an ice skater pulling in their arms. The original star might have rotated every few days. The neutron star can spin hundreds of times each second. Rapid rotation, plus an intense magnetic field, creates a powerful effect. The magnetic field funnels and accelerates particles, launching beams of radiation from the magnetic poles, radio waves, X-rays, gamma rays. Neutron stars are more than just cosmic curiosities. They are a frontier. They represent a boundary where our understanding of the universe is tested and often breaks down. These objects force us to confront the limits of our knowledge about matter, gravity, the fundamental laws of physics. What really happens inside a neutron star? Superfluid of neutrons? Or neutrons dissolve into quarks, gluons? We don't have the final answers. A bridge between the very large stars' galaxies and the very small, the quantum realm of subatomic particles. A neutron star is essentially a single gigantic atomic nucleus, 12 miles wide, held together by gravity. Studying them allows us to probe the strong nuclear force on an astronomical scale. Natural laboratories for extreme physics, insights we can't get on Earth. If left alone, it cools over billions of years, becomes a cold, dark ball of neutrons.